Hello viewers, Wagdaruna taking you through the story for A-level physics paper 1. And this video we're going to go through the topic of thermal radiation. So this topic is under the section of heat and heat properties and is suitable for students in both senior 5 and senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. And the student is expected to answer 5, but not more than 2 from any section. For example, if you pick 2 here and 2 here, then you'll pick 1 here. If you pick 2 here and 2 here, then you pick 1 here, like that. So 5 questions, but not more than 2 in any section. And on this platform, you have already completed the section of modern physics. That's why you see they are all ticked. And now we are on the section of heat. So the first part is done, second part is done, third part, fourth part, and now we are on this part of thermal radiation, or what we call black body. So we are interested in calculations on this platform, but complete notes are available in this book, Mastering A-Level Physics Paper 1. It contains clear notes, worked examples, and trial questions of the entire Physics Paper 1, that is mechanics, modern physics, and heat. So if you need a copy, contact the author on any of these 2 contacts. But a complete set of physics has 3 books. There is Physics Paper 1, Physics Paper 2, and the Topical Question Bank. Then you have Math Paper 1, Math Paper 2, and the Topical Question Bank. And for subsidiary math, it is only 1 book. Then Physics O-Level, there is O-Level Physics Notes, O-Level Physics Question Bank Topical, and O-Level Math Question Bank Topical. So for copies, contact the author on any of these 2 contacts. So now we shall start our topic of thermal radiation, or what we call black body. We shall see what it means. So thermal radiation is a form of energy emitted by a body in form of electromagnetic waves because of its temperature. So we are interested in a few theoretical parts which would help us to understand the calculations. That is why I told you, for complete notes you buy the book. So all bodies emit some kind of radiation. So this is a repetition, but the intensity and wavelength of the radiation varies depending on the temperature of the body. So with that, we can go to what we call black bodies. So this topic, thermal radiation in A-level, is mainly concentrated on black bodies, or the calculations. So we shall look at some of the definitions. So a black body is one that absorbs all, now this word, all radiations which fall on it without reflecting or transmitting any. So it absorbs all radiations but does not reflect or transmit any. That's what we mean by a black body. And examples of a black body can include 1, the sun, 2, the stars, and black holes, that is remnant of a star after it has used up all its energy. So we shall use mainly the sun and the star to act as a black body in the calculations. An enclosed blackened surface is also, with a small hole, is also a black body. For example, remember we said A black body is one which absorbs all radiations but does not reflect any or transmit any. So for example, if this is a small hole, radiation will enter here, but it will keep moving within this inside without moving out. So this small hole becomes a black body because no radiation is being reflected out of it. So now that we know what a black body is, we shall go to a black body radiator. So this is one which emits a radiation which is characteristic of its temperature and in particular which does not depend on the nature of its surfaces. So we have black body radiation now, that is the radiation from a black body. So we have looked at the definition of what a black body is. What about the laws that govern black body radiation? So there are two laws. The first one is Wein's law or Wein's displacement law, and it states that the wavelength lambda max is at which maximum amount of energy is radiated decreases with absolute temperature of the black body and is such that the product of this and this is equal to a constant. So such that this is supposed to be the product. So that means that this one, maximum wavelength, times this one, absolute temperature, when you multiply the two, it will be equal to a constant. And that constant is what we call Wein's constant. So this one is what we call Wein's constant, and usually in the examinations they will give you the value of this constant, so there is no need to memorize Wein's constant. Always look at the front page of your examination paper. This constant will be there. That means that if you know T, you can get lambda max because the constant will be given. If you know lambda max, you can get T like that. So let's first see how this formula can be used before we go to the second law of black body radiation. So the first question came from UNEB 2015 paper 1 question 7D Roman 3, and it says calculate the wavelength of the radiation emitted by a black body at 6000 Kelvin. Wein's displacement constant is that. So like I told you, this constant is always given. What you need to do is to quote this law that the product of lambda max times T is equal to Wein's constant. Then you come and substitute for T, which is given. T must be in Kelvin. The good thing here is already in Kelvin. If it was in degrees Celsius, we would first convert to Kelvin. Then here equate to Wein's constant, and we have one unknown, make it the subject, and that is what they wanted. Then question 2 came from UNEB 1992 paper 1 question 6F, and it says the element of an electric fire has a temperature of this. Calculate the frequency at which the intensity of the radiation by the element is maximum. So you know this from Wein's law. Come and substitute and get lambda max. So that is wavelength, but the question wants frequency. So you come and remember that frequency times wavelength is equal to speed of light in vacuum. Therefore, come and substitute this one is also a constant. It will be given in an examination. So what you do, you come and substitute for your lambda max and the constant, then get the value of F. And that's what they wanted. So that was the first law, Wein's law. Now we shall go to the second law, which is Stefan's law. So this law states that the total energy radiated by a surface area of 1 meter squared of a black body per second, know that word, black body per second, is directly proportional to the fourth power of its absolute temperature. So what does that mean? It means that E is proportional to T to power 4. That's what they meant by fourth power, T to power 4. When I remove the proportionality sign and I put an equal sign, I have to put a constant of proportionality. So in this case, the constant of proportionality is sigma. And that sigma has a special name. It's called Stefan's constant. And also has a value. This value which is given all in an examination. So Stefan's constant is 5.67 exponent negative 8 watts per square meter per Kelvin raised to power negative 4. Sorry, per fourth Kelvin. So what does that mean? It means that if a body, remember this one was for a body of surface area 1 meter. What if the surface area of a body is capital A? It implies that the total energy radiated per second will be E total, which is sigma or Stefan's constant times the surface area times the temperature raised to the power 4. But energy radiated per second is equal to power. Thus, the power radiated by the black body is given by that. So this expression is very, very vital. We're going to use it more frequently. So you should remember that power radiated is equal to Stefan's constant times area, surface area times the temperature raised to the power 4. Okay, now that we have seen the temperature, the expression for power radiated, let's go to heat exchanges for a black body in an enclosure. So here we shall consider a black body whose absolute temperature is capital T in an enclosure at absolute temperature T0. So T0 is the temperature of the enclosure and T is the temperature of the body, black body. So we shall illustrate it. So that is the black body at temperature T, and this is the enclosure at temperature T0. Therefore, the rate of loss or gain of heat stroke radiation from a body depends on the temperature of its surroundings. So if this temperature is bigger than this temperature, it means that the body will gain from the surrounding. But if the temperature of the surrounding is smaller than the temperature of the body, it means that the body will lose to the heat to the surrounding. So there are two conditions. If T is greater than T0, the black body loses energy by radiation to the surrounding until dynamic equilibrium is reached. And at dynamic equilibrium, the rate of energy lost is given by that. So what changes here, instead of writing just T from in the equation for power radiated, in the expression for power radiated, we write the difference. So this was T to power 4 minus T0 to power 4, because T was bigger than that. If T0 was bigger, then we would have begun with T0 minus T. So if T is less than T0, the black body gains heat energy from the surrounding until dynamic equilibrium is reached. And at dynamic equilibrium, the rate of energy gained is given by that. So then you realize that now we just interchange T0 minus T. So the assumption made is that the body is a black body. So here there was something missing. You should put the word black body, and that the interchange of energy is by radiation. So the body must be a black body, and the interchange of heat is by radiation. So with those, we shall go through some questions. Question 1 came from UNEB of November 1998, paper 1, question 6D, Roman 2, and it says, calculate the rate of loss of heat energy of a black body of area 40 meters squared at a temperature of 50 degrees Celsius. If the radiation it receives from the sun is equivalent to the temperature in space of negative 220 degrees Celsius. So first of all, you have to convert the temperatures to absolute temperature. So this was Celsius, you convert it to Kelvin to give you this. Also this one, convert it to Kelvin to give you that. Then you can quote the formula. Because here now T is bigger than this, so it will be T minus T naught. That's why you see a T to the power 4 minus T naught to the power 4. Then we can substitute. Substitute Stefan's constant is a constant and it is given in the question. It's given in every examination. This is the surface area, which is that, and this is T. This is T naught. Then you can use a calculator to come up with the power lost. And the calculation they wanted you to calculate the rate of loss of heat. So rate of loss of heat is the power lost. So that is what they wanted. Question 2 came from UNEB 2009, paper 1, question 7E, and it says, a small blackened solid copper sphere of radius 2 centimeters is placed in an evacuated enclosure whose walls are kept at 100 degrees Celsius. Find the rate at which energy must be supplied to the sphere to keep its temperature constant at 127 degrees Celsius. So first you'll get the area or the surface area. So surface area of a sphere is 4 pi r squared. So the radius is 2 centimeters, convert to meters to give you 0.02. Then convert this temperature in Celsius to Kelvin to give you 400 Kelvin. Then also convert this to Kelvin to give you that. So then we shall now quote the power supplied is equal to Stefan's constant times surface area in brackets T to the power 4 minus T naught to the power 4. Then you'll come and substitute Stefan's constant, surface area, which is this, then T is there, T naught is there. Simplify, you'll come up with that as the power supplied, and that's what they wanted. Question 3 came from UNEB 2018, paper 1, question 6B, and it says, a copper sphere of radius 7 centimeters and density 900 kg per meter cubed is heated to a temperature of 127 degrees Celsius and then transferred to an evacuated enclosure whose walls are at a temperature of 27 degrees Celsius. Calculate Roman 1 the net rate of loss of heat by the copper sphere. Then Roman 2 the temperature of the copper sphere after 5 minutes. So the specific capacity of copper is that. So you start with Roman 1. Roman 1, so area or surface area of a sphere is 4 pi r squared. So it gives that. Temperature, convert this to Kelvin. Convert this to Kelvin and also convert this to Kelvin. Then you quote the formula and substitute. When you substitute, you come up with this as the rate of loss of heat, and that was Roman 1. For Roman 2, they want the temperature of the copper sphere after 5 minutes. So first of all, mass of the sphere is volume times density. So come and substitute volume of a sphere is 4 over 3 pi r cubed. Density is rho. So the good thing, we are given the density of the sphere as 900, radius was given as 0.07, so we'll come up with this as the mass of the sphere. Therefore, average rate of heat lost is equal to this plus 0 over 2. Remember, if you go back in this one, this is the rate of heat lost, net rate. Therefore, the average will be this plus 0, which was the initial, to give you divide by 2 to come out will be equal to quantity of heat over time. So quantity of heat, you'll come and substitute. Mass is there, specific capacity is there, theta 2 is there, theta 1 we don't know it, time is 5 minutes, convert to seconds. Then next is to simplify, open brackets, and make theta 1 the subject to give you the answer they wanted. Then question 4 came from UNEB 2003 paper 1 question 7c, and it says Roman 1, a spherical black body of radius 2 centimeters at this is suspended in an evacuated enclosure whose walls are maintained at 27 degrees Celsius. If the rate of exchange of thermal energy is equal to this, find the value of Stefan's constant. And Roman 2, calculate the wavelength at which the radiation emitted by the enclosure has maximum intensity. So we shall start with Roman 1. Roman 1 area is that, temperature convert to Kelvin, then quote the formula, substitute for power gained. This one is what they want, cross-section area, T naught T. Next is to look for a way of making sigma the subject. So make it the subject, it will be that, and that's what they wanted. Then for Roman 2, they wanted to calculate the wavelength at which the radiation emitted by the enclosure has maximum intensity. So from Wein's law we have that, then you substitute and get lambda max. Then question 5 came from UNEB 2003 paper 1 question 6d Roman 1, and it says a solid copper sphere of diameter 10 millimeters and temperature 150 Kelvin is placed in an enclosure maintained at a temperature of 290 Kelvin. Calculate, stating any assumptions made, the initial rate of rise of temperature of the sphere. So density of copper is that, and specific heat capacity of copper is that. So cross-section area, so surface area of the sphere is that. Remember, this was the diameter, so to get the radius we divide by 2. Then we have this, and we have this as T naught for the enclosure. Therefore, assuming that the sphere radiates as a black body, and that the heat exchange is by radiation only. So I think we are writing this because here the equation they told you calculate, stating any assumptions made. So we have to make this assumption that the sphere radiates as a black body and that heat exchanges only by radiation. So when that happens, it implies the net power absorbed is given by this formula from Stefan's law. Then you will substitute and get the answer they wanted. So that was the net, but here they said initial rate of rise of temperature of the sphere. So I've got the net power absorbed. What about the rate of rise in temperature? There we shall come and say mass is equal to density times volume, which is that. Substitute for density, substitute for radius to come up with this mass. So now we shall come and say that rate of heat absorbed by copper is equal to the net power absorbed. Therefore, rate of heat absorbed by copper is MC, change in temperature over time, is equal to this net power which we got in the previous slide. Then come and substitute for M, substitute for C, and this is what they want. This one remains. So look for making it the subject. You'll come up with that as the answer. So now shall go to emissivity of a body. So emissivity is the ratio of the total power radiated per square meter by a given body to that red emitted by a black body at the same temperature. Therefore, emissivity is given by this symbol and is equal to total power over power by the emitted by the black body. That means that when I cross multiply, total power is equal to emissivity times the power emitted by the black body. And we saw that power emitted by the black body is given by this. So what you do, you add on this emissivity to get the total power. So with that, we shall go through some questions. Question 1 came from UNEB 2006 paper 1, question 7C, Roman 2, and says a metal sphere of radius 1.5 centimeter is suspended within an evacuated enclosure whose walls are 320 Kelvin. The emissivity of the metal is 0.4. Find the power input required to maintain the sphere at a temperature of 320 Kelvin if the heat conduction along the supports is negligible. So surface area is given by that, then power input is given by that. Now there is emissivity. Then we shall come and substitute emissivity, area, Stefan's constant, T and T naught. So this one alone will make the whole term to be 0. Therefore, the power input is 0 watt. Question 2 came from UNEB 2010 paper 1, question 7E, and it says a tube a tube of side 1 centimeter has a gray surface that emits 50% of radiation emitted by the black body at the same temperature. If the tube's temperature is 700 degrees Celsius, calculate the power radiated by the tube. So surface area of the tube is, remember, a tube has 6 faces, and this face has the same area. So it will be 6s squared, and s is the side, so to give you 6 exponent negative 4 meters squared. Temperature, it was in degrees Celsius converted to Kelvin. Then power radiated is given by that. Because of this 50% means there is emissivity. Therefore, you come and substitute emissivity is 50%, Stefan's constant, cross-section area, or sorry, surface area, and temperature. Use the calculator, you'll come up with that. So now we shall go to emission and absorption of heat energy by planets in the universe. So something we need to know about, some theory we need to know about these planets in the universe. One is that the sun is the center of the universe. That is one. So it should always be remembered that the sun is the center of the universe and the planets revolve around the sun in elliptical orbits. Then you should also know that the sun and the planets are assumed to be perfect spheres. So it is not true that they are perfect spheres, but in the calculations we assume that the planets and the sun are perfect spheres. Then the sun is also considered to be a black body. I think remember under the examples of black body, I brought up the sun. So the sun is considered to be a black body since the gases at its surface will absorb any radiation incident on it. And because it's a black body, it means that it is assumed to radiate heat, so it is assumed to radiate heat as a black body. Because of this, because of it having gases which absorb incident radiations, it will be assumed to radiate as a black body. Remember, black body, it absorbs all radiations but reflects none. The planets are also assumed to absorb and emit radiations as black bodies, which are seen in the calculations. Therefore, the figure below shows a sketch of one of the planets revolving around the sun in the universe. So let's first make an illustration for you to easily understand the part we are on. So we have the sun of radius Rs. So when you see Rs, it denotes radius of the sun. Then you have a planet of radius Rp, and these are separated by a distance Rsp, which is distance between the sun and the planet. So this sun is radiating in all directions. That means that what we receive, the radiations will be in form of a sphere, like the way if you get a hollow ball. So the sphere, this is the spherical part where these radiations radiations from the sun will reach. And for you to get this orbit, you'd base on the distance from the sun to the planet. That's why you base on to get this sphere, or what we call the orbit of the planet. So Rs, radius of the sun, Rp, radius of the planet, R. So here it is Rsp. Here you put Sp. So Rsp is the mean distance between the sun and the planet. So what does that mean? It means that the surface area of the sun is given by this. Remember, surface area is 4 pi r squared, and the radius of the sun is Rs. What about that of the planet? It will be 4 pi Rp squared, because radius of the planet is Rp. Okay. Then the total area on which the sun's radiation falls at a distance Rsp from the sun where the planet is situated is given by Asp, which is 4 pi r squared. So 4 pi Rsp squared. So this one, if you go back here, so this sun emits a radiation band. All these radiations are received by this sphere. So that is what we call the total radiation. The area which is received, that's what we called Asp, and it is 4 pi Rsp squared. Now you realize that this planet receives only a fraction of the total radiation from the sun. This planet receives only a fraction of the total radiation from the sun. The total radiation of the sun is received throughout this sphere. Therefore, to get the radiation for only this, you use a fraction of the total, as we shall see in the calculation. So now we shall go to deriving some of the formulas to be used. So one will be the power radiated by the sun. We remember from Stefan's law, we derived the expression for power radiated. So that's what we shall remember. So the total power radiated by the sun will be given by PS equal to Stefan's constant, surface area, and the temperature of the sun. So this AS is the surface area of the sun, and this Ts is the temperature of the sun. And this surface area of the sun, you have already saw that it is 4 pi Rs squared. So this is the expression for the power radiated by the sun, the total power. So Ts is the temperature of the surface of the sun. So with that, let us go through some of the questions to easily memorize that formula. So question 1 came from UNEB 1996, paper 1, question 7D, Roman 2, and it says the total power output of the sun is this. Given that the mass of the sun is this and its density is this, estimate the temperature of the sun and state any approximations made. So Stefan's constant is always a constant and it is given, which is that. So first we shall interpret the question. This will be the mass of the sun, then density of the sun, and the power radiated by the sun, or the power output. So we know that volume is mass over density, therefore volume of the sun is the volume of the sphere, which is 4/3 pi r cubed. So r is radius of the sun, is equal to mass, which is this, divided by density, which is that. So that means that I have only Rs as the only unknown. Therefore, when I make it the subject, I'll come up with the radius of the sun as that. Therefore, now total power output of the sun is equal to area, surface area times Stefan's constant times temperature of the sun raised to the power 4. So I'll come and substitute. Total power is that, it was given 4 pi is here, r is here, it is squared, Stefan's constant, and Ts to power 4. So Ts is the only unknown, therefore I can easily make it the subject. And that will be the answer they wanted. So the assumption is that it is assumed that the sun is a perfect black body and that it's spherical in shape. So that was power radiated by the sun. What about energy intensity of the sun, or solar constant, or solar flux? All these three words mean the same. Energy intensity, solar constant, and solar flux. They all mean the same. So what is it? Energy intensity, in short, it is energy per second. So total, this is the power or energy per second radiated by the sun that falls on an area of 1 meter squared. So energy intensity is energy per second when the area is 1 meter squared. Area has to be 1 meter squared. Therefore, energy intensity is equal to power radiated by the sun divided by surface area of the orbit of the planet of the sun. Therefore, E int is the same simple word form for energy intensity is equal to PS over ASB. So this should be P to mean planet. PS, we already saw this formula, and ASP, we already saw that formula. So next is to cancel out. I can cancel out the 4 pi. Then this one doesn't have any power. Then this one has a power 2, and this one also has a power 2. I can combine them to give you that. Everything raised to the power 2. Then you have Ts to the power 4, which is here. So this will be the expression for energy intensity. Stefan's constant, radius of the sun over radius of the mean distance between the sun and the planet, and everything squared, times the temperature of the sun raised to the power 4. So when we say us using this formula, it means we are getting energy intensity. And for you to easily grasp this formula, let's see some of the questions. Question 1 came from UNEB of March 1998, paper 1, question 7D, and it says, consider the sun to be a sphere of radius 7 exponent 8 meters, whose surface temperature is 5900 Kelvin. Roman 1, find the solar power incident on an area of 1 meter squared at the top of the Earth's atmosphere if this is a distance of 1.5 exponent 11 meter from the sun. So this is now the distance between the sun and the planet. Assume that the sun radiates as a black body. Then Roman 2, explain why solar power incident on 1 meter squared of the Earth's surface is less than that calculated in D Roman 1. Okay, so we shall start with Roman 1. Roman 1, let us first make an illustration. So we have the sun of radius RS, then we also have the earth of radius RE, then we have the distance, mean distance between the sun and the earth, and it is now RSE. So this RSE is the distance between the between the sun and the earth. This one is the radius of the sun and the temperature of that sun. So solar power incident on an area of 1 meter squared is the same as energy intensity. So like I told you, energy intensity as area has to be 1 meter squared. And we know that formula of energy intensity is given by that. Therefore, shall come and substitute Stefan's constant, radius of the sun over radius of the distance between the earth and the sun. Then temperature of the sun raised to power 4. Then when I simplify, I'll come up with that as the solar power they wanted. Then for Roman 2, they want you to explain why solar power incident on 1 meter squared of the Earth's surface is less than the one calculated. So you have calculated this as the solar power, but the actual one is less. Why is it so? So it is because solar radiation incident on the atmosphere is partly absorbed by the atmospheric gases and partly scattered. This accounts for the difference. So some of it is partly scattered, therefore it will be less. Then question 2 came from UNEB 2008 paper 1 question 7C, and it says the energy intensity received by a spherical planet from a star is this. The star is of radius this and is this kilometers from the planet. Roman 1, calculate the surface temperature of the star. Roman 2, state any assumptions made in Roman 1. So still we shall make a sketch. We have the star, we have the planet, and we have the distance between the two, which is RSP. Okay, so in this case, this one is the distance between the two, and this one is the radius of this, and this one is the energy intensity. So you come and interpret that RS is that, change it to meters, RSP is that, change it to meters. Then energy intensity was given as that. So you shall come and remember that energy intensity is given by this formula. Then you shall come and substitute. Where there is energy intensity, put there this, Stefan's constant, then radius of the sun, then radius of the distance between the sun and the planet. Now we are dealing with the star. So this is the radius of the star, and this is the radius of the distance between the star and the planet. Then the temperature of the star is what they want. So shall come and simplify. Then collect, like, put Ts on one side, then Fourth root will be that, and that will be the temperature they want. Then Roman 2, they want you to state any assumptions made. So it is assumed that the star radiates as a black body and that it's a perfect sphere. It's also assumed that there is no heat lost to the space. So those are the two assumptions they wanted. Then question 3 came from UNEB 2014, paper 1, question 6D, Roman 2, and says the Earth receives energy from the Sun at a rate of this. If the ratio of the Earth's orbit to the Sun's radius is this, calculate the surface temperature of the Sun. So here still we shall sketch the Sun, the Earth, then the distance between the two. Okay, so the energy intensity we are given as that, and the ratio, they gave us the ratio of the Earth's orbit to the Sun, that is RSE, Earth's orbit to the Sun's radius is that. So Earth's orbit is this one. I think you remember the sketch we drew at first, there was an orbit here where the Earth is. So that's what they mean by the Earth's orbit, and the radius is that. And the Sun's radius is this RS. So this over this gives you 216. Therefore, when I cross multiply, I take this one this side, I'll come up with RSE being equal to 216 RS. Okay, so I'll come here and quote my formula for energy intensity. After quoting the formula, I'll begin substituting. Energy intensity is that, Stefan's constant is that, then RSE I'll put there this here. Okay, now from there I realize that this and this cancels. So when it cancels and you simplify, this divided by 216 gives you this. Then this one is maintained here, and this one is also maintained here. Okay, now the good thing, it is only TS which is the only unknown, so I have to look for a way of making it the subject, and fourth root of that gives you the temperature of the Sun, which they wanted. Okay, so that was energy intensity. Another formula we need is the one for rate of loss of mass of the Sun. So when the Sun radiates heat, its total mass decreases, and the decrease in mass is known as the mass defect, which is delta M. So the expression relating mass defect and the total power radiated by the Sun is given by this. PS is equal to mass defect times speed of light in vacuum squared. C is the speed of light in vacuum and has a value this. So it's a constant, it will always be given in an examination. Therefore, the total loss of mass by the Sun is given by this. So when I make this the subject, I'll come up with PS divided by C squared. So with that, we shall go through these questions. Question 1 came from UNEB 2001, paper 1, question 5B, and it says, a flux of solar energy incident on the Earth's surface is this. So this is the energy intensity. Calculate Roman 1, the temperature of the Sun, or the surface of the Sun. Roman 2, the total power radiated by the Sun. And Roman 3, the rate of loss of mass of the Sun. So we shall start with Roman 1, but still it is easier to sketch for you to easily understand what you're doing. But sketching is optional, though it makes the work look neat. So we shall quote the formula for energy intensity. You all know this formula. Then substitute. Now here I use the word SP, but it should be SE to mean distance between the sun and the earth. So substitute energy intensity, Stefan's constant, RS, RSE, and this is the only unknown. So still the same, simplify and make T to power 4 the subject, and after that we make Ts the subject. And that will be the temperature they want. So that was Roman 1. Now we shall go to Roman 2, where they want the total power emitted by the sun. So total power emitted by the sun is area, surface area times Stefan's constant times temperature to power 4. So come and substitute and get the answer they wanted. Then Roman 3, they want the rate of loss of mass by the sun. So now that energy is that, therefore that means that power is equal to energy over time. Therefore power is equal to change in mass over change in time times c squared. So that means that when I make this one the subject, I'll come up with PS over c squared. So PS is that we already calculated, this is the constant, you come up with this as the rate of loss of mass. So now we shall go to what we call Prevost's theory of heat exchanges. So this theory states that when a body is in thermal equilibrium with its surrounding, its rate of emission of radiation to the surroundings is equal to its rate of absorption. So the rate of emission is equal to the rate of absorption of radiation energy from the surrounding. So that is what we call Prevost's theory. Rate of emission is equal to rate of absorption. Therefore, from Prevost's theory, it implies that a body at constant temperature radiates heat radiations at the same rate as it absorbs heat radiation. For example, if I have a planet and here there is a sun, this sun will radiate heat to reach this planet. So this Prevost theory means that the rate at which this planet receives the heat is the same rate at which it also radiates. Hope it is understandable. So this sun sent radiations to this planet, and this planet absorbed this radiation from the sun at a certain rate. Now Prevost's theory means that the rate at which this planet absorbs this radiation is the same rate at which the same planet radiates the radiations it had absorbed. And also there are some formulas which we need to go through. So one is the power received or absorbed by a body. So previously we saw power radiated by the sun, but now we are looking at power received by the body, because this previous theory has rate of emission and also rate of absorption. So it means that it receives radiation and it also radiates the radiation it has received. So we need to know the power received and also the power radiated. So let's start with this power received or power absorbed. So here we shall come and say that since intensity is the power received by 1 meter squared of a body, it implies that the total power received by the body is the product of energy intensity of the radiator and the area of the body receiving the radiation. So each time they talk about power received, you must think of energy intensity and the area of the body receiving the radiation. So mathematical shows that P received is equal to E intensity or energy intensity times the power surface area of the body receiving the radiation. Okay, so let's go through this question to master the formula. Question 1 came from UNEB 2002, paper 1, question 6D, Roman 1, and says, an element of a 1 kilowatt electric fire is 30 centimeters long and 1 centimeter in diameter. If the temperature of the surroundings is 20 degrees Celsius, estimate the working temperature of the element. So here we shall need a sketch. So we have this, it is in form of a cylinder radius and length. Therefore the surface area is the surface area of this, the surface area of the part which is radiating is this. So it will be 2 pi RL. I think remember that in your O-level math. So come and substitute 2 pi, then R is half this diameter. Then the length is 30 centimeters, convert to meters to give you this. So assuming radiative equilibrium, power radiated by the filament is equal to power received by the filament. So power radiated is this. You remember that in the previous slides, power radiated is area times surface area times the Stefan's constant times the temperature to power 4. And this power received is this power received by the filament. So it was 1 kilowatt, is now you have to convert it to watts to give you 1 times 10 to the power 3. Then you come and substitute for area, for Stefan's constant, and this is the unknown. This one is maintained. So T is the only unknown, so simplify and then make T to power for the subject and then make T the subject. So that will be the temperature of the element. Then question 2 came from UNEB 2019 paper 1 question 5B, and it says a cylindrical metal rod with a well insulated curved surface has one end blackened and then exposed to thermal radiation from a body at a temperature of 500 Kelvin. If the equilibrium temperature of the blackened end is 400 Kelvin and the length of the rod is 10 meters, calculate the temperature of the other end. Thermal conductivity of the metal is that. So still here we shall make a sketch. They said it is well insulated, so that the insulations so it has temperature at the ends, theta 1 and 400 Kelvin. And this radiation is 500 Kelvin. Okay, so they said if the equilibrium temperature of the blackened end is 400 and the length of the rod is this, calculate the temperature of the other end. So this temperature, what you need to know is that the rate of heat flow is the same. So we shall come here and say that assuming radiative equilibrium, power absorbed is equal to power conducted. So power absorbed is equal to this, the net power absorbed, and this is the power conducted through the material. I think you remember this formula under thermal conduction. We saw it in the previous video. So we'll come and substitute Stefan's constant, area, we don't know it. Then this one's T minus T naught, thermal conductivity, cross-section area, then change in temperature, divided by the thickness. So the good thing is that A can cancel and remain with theta 1 as the only unknown. So when you do that, you shall come up with that after simplifying, opening brackets, and make theta 1 the subject. You shall come up with that as the temperature they wanted. So we have been dealing with power received by a body, just any body, but what if it is a planet in particular? How do you deal with such? So the concept is the same, but we add something else. So here the total power received by the planet is the product of the energy intensity of the sun and the circular cross-section area. This is area of the planet. So this is the unique part we add in. Previously we were just surface area, but now we base on circular cross-section area, provided it is a planet. So that means that the total power received by the planet is equal to energy intensity times the circular cross-section area of the planet. So mathematically it will be P received is equal to energy intensity times area of the circular part. And energy intensity, we already saw that it is the whole of this. Then the circular area is pi r squared, area of the circle. And that will be the formula we shall use provided they want power received by a planet. So circular cross-section area of the planet is the effective area of the planet on which the sun's radiation is incident normally. Now the question is, why do we use circular? So if that is the planet and this is the sun, the radiations received, if I look from this side, it will be that fraction. So this other part will not receive any radiation. So it will only be this half of it. And half of it, if you look from this side, it will be a circle. That is why you use the word circular. We shall see questions on that, but let's first look at this temperature of the planet, because they go hand in hand. So temperature of the planet can be calculated by assuming that there is radiative equilibrium between the power received by the planet and power radiated by the same planet. I think you remember that in Prevost's theory. So assuming radiative equilibrium, power received is equal to power radiated by the same planet. So power received, what is the formula for power received? Power received, we have seen it that it is energy intensity times the circular cross-section area. Then power radiated is surface area times Stefan's constant times the temperature raised to the power 4. So when I equate the two, I'll be able to make Tp the subject, and that will be the temperature of the planet. So when I try to simplify, simplifying this will cancel with that, okay. Pi will cancel with this pi, okay. Then Rp squared cancel with this Rp squared. Then I'm going to remain with this one, which is here. Then this one, which is here, and this 4, which is there, and this Tp to the power 4, which is there. So Tp will be the temperature of the planet which they want. So when I make it the subject, I'll be able to get the temperature of the planet. So with that, we shall go through these questions. Question 1 came from UNEB, 1999, paper 1, question 5D Roman 2, and it says, assuming that the sun is a sphere of radius this, at a temperature of this, Estimate the temperature of the surface of Mars if its distance from the Sun is that. Okay, so here we shall also make an illustration. That is the Sun, and that is our Mars, which is the planet, and that is the distance between the Sun and the planet, which is Mars. Okay, then Ts is the temperature of the Sun, Rs is the radius of the Sun, Rsm is the distance between the Sun and the planet. So power received by Mars is equal to energy intensity times circular cross-section area. So this is energy intensity and this is the circular cross-section area. Take note that it must be circular. Then power radiated by Mars is surface area. So this was circular cross-section circular area, but this one is surface area times the energy, Stefan's constant, times the temperature of the mass raised to the power 4. Okay, so now at equilibrium we shall equate the two, power received and power radiated. So here it is not Pluto, it is Mars, power radiated by Mars, not Pluto. So substitute this is the power received, power radiated. Then shall simplify and then substitute Rs, Rsm, Ts, and Tm is the only unknown. So make it the subject, simplify, make T to power 4 the subject, and then make Tm the subject. And that will be the answer they wanted. Then question 2 came from UNEB 2006 paper 1 question 70 Roman 2, and it says the average distance of Pluto from the Sun is about 40 times that of the Earth from the Sun. Okay, if the Sun radiates as a black body at 6000 Kelvin and is 1.5 exponent 11 meter from the Earth, calculate the surface area, the surface temperature of Pluto. So we shall illustrate also. That is the Sun, that is the planet Pluto, then the distance between them. Okay. So temperature of the Sun is that, radius of the Sun is that. Now here they have told us that, let's see here, that the average distance of Pluto from the Sun, that is RSP, is 40 times, that is this 40 you're seeing here, that of the Earth from the Sun, 40 times RSE. And they've given us the distance of the Earth from the Sun, which is this. Therefore, RSP is 40 times that distance of the Earth from the Sun, to give you this. So power received by Pluto is given by that in energy intensity times circular cross-section area, which is that. What about power radiated? Area times Stefan's constant times temperature raised to the power 4. Then at equilibrium, we are going to equate the two. When we equate the two, we shall come up with that. Then we simplify and then substitute. Then look for making Tp the subject, and Tp will be the temperature they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on kinetic theory and gas laws. So if you're not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so you can all benefit us a family.